Okay, folks, I can see we just hit 1 minute after the hour, so we're going to go ahead and get started. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and is co-organized with contributions from myself, Stephen Slaughter, and Jamie Kostelnik. And for those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of Kate's talk today to take questions. So in the meantime, please just do the best you can to make sure your microphone is muted and your video camera is off when you're not intending to speak. Dave, I'll go ahead and turn it over to you. Thank you so much.
Thanks, Matt. Hi, Kate. Hi, everyone. My pleasure to introduce Kate Allstadt. I directly supervise Kate, but I'm not always aware of what she's doing because she's half in the landslide program and half in the earthquake program, which practically speaking means she spends about 75% of her time in the earthquake program and 75% of her time in the landslide program, where the expectations are both high because she does such great stuff. She's really, by definition, multidisciplinary, being in these two different programs, but also she continues to work with volcano programs. So Kate's got talents on both the landslide and seismology front, and for that reason, she's in demand. She's actually covering only a small part of what she works on, and that's the real-time earthquake induced landslide and liquefaction. But she could probably give a seminar every week for the next couple of months on the other things she's doing. So a little background, education-wise, Kate got her BS in environmental geology Northeastern, got a master's degree in engineering seismology in Europe at Grenoble and Pavia Rose School, and then did her PhD at UW with both the seismology and also engineering group there, and went on to do a postdoc, staying on at Washington for a while, working and coordinating the M9 project as it got started, and then went to Cascades Volcano Observatory after that under NSF before we snatched her here down in Golden, and have the honor to work with her since. Like I said, there's a broad range of expertise that Kate brings, and part of that is just plain seismology. She was actually a network operator in real-time seismology at UW, and so she's got the seismology and operations down, but she also works on landslide modeling and monitoring, and is involved with our real-time products as well. But I think also fundamental coding and software development. A nice couple of projects she's been doing in the past include everything related to seismoacoustics and weird sources, volcano, glacial, and rock slide and other sources that she's been studying. And then lastly, as a mentor, she's got a lot of students, interns, undergrads, grads, and PhD and postdocs that she's mentored, and they've gone on to do really neat stuff. And she is the co-founder of a even younger group of interns at the GeoGirls program that she started several years back, and it's still going on every summer. There's a week course for kids girls in the Pacific Northwest at Cascades, at Mount St. Helens, and Kate's still coordinating and going out for a week every summer to participate in that great mentoring program. So, Kate, I'll leave you a couple minutes to talk, and really glad to hear from you.
All right, thank you, Dave. It's always weird to have to sit and listen to someone say nice things about you, but I appreciate it. So thanks everyone for joining today. I know it's the middle of the field season, so I'm glad that you're able to make it. So today I'm going to talk about one of the newest near real-time earthquake products that the USGS produces, and that's the ground failure product. And so we released it publicly about 3.5 years ago. And so today I'm going to kind of talk about, the product itself and how we developed it and how it works, and also talk about how it's been doing for the past few years. And then I'll end with, I'm going to touch on a bunch of work that people here at the USGS and some of our collaborators are doing to kind of build on and expand and improve the product that we currently have released. So I will jump in. So let's see. Oh, there we go. Okay, so the first part of the talk, I'm I'm going to basically talk about the fundamentals of the product, and a lot of the material comes from this paper that we published in Earthquake Spectra about just over a year ago. But I've updated a lot of the numbers to bring us up to the present. So I just wanted to acknowledge all my co-authors on that paper who are listed here, especially Eric Thompson, who kind of co-leads this project with me, and then obviously also Dave Wald, whose initial idea of this product actually was, so that he kind of made this happen. But there's also lots of people who have contributed along the way and are contributing to ongoing research, and so I've listed a lot of them on the right, and I'm sure there's many more that I could have listed because I hope that I'll make pretty clear to you, just how much goes into a product like this. Even though it's, seems relatively simple, there's a lot of science and a lot of development and research, code development, design, all sorts of things that go into it, and lots of people have contributed to that. Okay, so just to step back a little bit for a little bit of an overview of earthquake-triggered ground failure. So why should we care about this? So one big reason is that it's a major contributor to earthquake losses for some major earthquakes. There's a lot of well-known cases you may have heard of, such as the Wenchuan earthquake in China, where 20,000 people were killed by landslides. So it's a source of fatalities, a source of damage, but it also can kind of interfere with the response and recovery by basically throwing a wrench in things. It can block roads. This is an example from the Northridge earthquake in California. Can block and damage roads sometimes for long periods of time. It can cause damage to infrastructure. Liquefaction in particular can cause damage to subsurface infrastructure. This is an example from Christchurch, where a lot of their, they didn't have water and pipelines and sewer in some parts of the city for a really long period of time, which makes it hard to recover from the earthquake. It also can damage ports. This is an example from the 2010 Haiti earthquake, and that's a problem, because it makes it a lot harder to bring, goods in right after the earthquake, but also in a long-term sense, it can cause economic damage. And it just generally, causes a lot of problems. And it's not, it's not every earthquake that has dramatic ground failure like this. And kind of that's part of what we want to do with this tool, and then I'll talk about in a little bit, is we want to be able to identify relatively quickly when ground failure is likely to be a big problem and when it probably won't be a big problem. Here's just a few other more recent examples. These earthquakes keep happening and the ground keeps failing. So these are just some more recent examples from Hokkaido in Japan. There are a lot of landslides that killed some people, also really dramatic liquefaction. We have a bunch of earthquakes in the US over the past couple of years that caused ground failure, including the Anchorage earthquake and the Puerto Rico earthquake. And there's been some really, I don't know what the word is, really sad cases of ground failure in other parts of the world, especially this event in Palu, Indonesia, and I'll show a little bit more of that coming up. So it can be a real tragedy, but it's not always a problem in every earthquake. And so part of what we want to do with this tool is to quickly identify when it's going to be a problem and where the problems are likely to be. And that's really helpful to do in a near real-time sense. And so by that, I mean within tens of minutes to sometimes a few days, because it can often take a lot of time to even know what happened after an earthquake. It's satellite imagery takes time to come in. There can be clouds. It takes time for people to look at it. It's difficult to get around on the ground a lot of the time. So it can take quite a while to actually know what happens, but decisions still have to be made in the meantime. So we're just trying to provide, early estimates as early as possible to help inform some of that decision making until we know what actually happened on the ground. Okay, so this is a timeline of all the USGS earthquake products. This is the earthquake information system. So ground failures here at the right. And so the products on the left, like the probabilistic maps and the scenarios, those are useful before the earthquake. Then we have the products right when the earthquake happens, such as earthquake early warning, and then the location, magnitude, mechanism and so on. And then the near real-time products are at the right here. So those are after the earthquake happens, once we have the magnitude and location. Then we start producing these other products, and then we keep updating these as more information comes in. So you're probably familiar with some of these products, and I won't talk in great detail about most of them. I'm going to just focus in on the ones that relate to ground failure, because these products kind of connect to each other. So at the core of the near real-time products is the shake map. So that's shown in the center here. And the shake map is basically this spatial estimates of shaking. So different shaking parameters like peak ground acceleration, peak ground velocity, spectral accelerations, and so on. And so the shake map product at its core uses ground motion prediction equations that have been published by many, many different people. So it uses the most appropriate set of those equations to estimate the shaking based on the magnitude and location and earthquake type, but then it gets updated with strong motion data. So if there's seismometers in the area, those get added and it gets updated, and also felt reports. So that's this product at the left called Did You Feel It? So this is where you can go in and report what the shaking was, and that gets fed into ShakeMap and makes it better. And then also for larger earthquakes, we want to put the fault geometry in there, and that can make a big difference. And we can get that from teleseismic inversions of global seismic data and also from INSAR results. Okay, so we have our shake map and it keeps getting updated as more data and constraints come in. And then that feeds into these other products. And so the one at left is called ShakeCast. And so you don't really see this publicly because this is for different organizations to run on their own servers where they can put their facilities in, like their bridges or their power plants. And basically they set up their facilities in there and set up some choices about alerting, and it basically can help them prioritize inspections after an earthquake occurs. The pager product produces order of magnitude estimates of fatalities and economic losses. So you've probably seen that, or you've at least seen the numbers reported in newspaper articles. And then ground failure at right also at its base comes from the shake map. And so all three of those are based on the shake map. As the shake map gets better, then those products get better over time. And then at present, Pager and ShakeCast do not currently include ground failure losses in them. And so that's something that we're aiming towards, but we're not there yet. So currently Pager and ShakeCast are only from shaking directly. Okay, so I threw together a timeline here, and I'm not gonna go over it in great detail, but I just wanted to get across like just how much time and effort it takes to make a new robust operational product. So this effort started in 2012, so that's before I even worked here, and there was a couple of graduate students that started developing the models that we needed to make this product, because they did not exist before. And so from 2012 to 2017, we had these two PhD students who are leading this effort to develop those models. So that took several years, but then on top of that, we had to develop all sorts of software, and we had to design the product. We had to do internal testing. We had working groups. We had lots of iterations of product design, software releases. So it's really an involved process, even for a relatively simple product. And it's still ongoing because currently we're working on moving the product to the cloud, and that's not trivial either. So yeah, I guess the point of this slide is that it takes a lot of time and effort to make something that's going to run operationally within the USGS. Okay, so next I'm just going to show you the product if you haven't seen it yet, just kind of give an overview of what it looks like, and then we'll get into the guts of it a little bit, and then we'll go on from there. So this slide is a screenshot of the USGS earthquake page. This is for the 2018 Anchorage earthquake, and you can see a lot of those products we were talking about earlier have their own separate cards on here. And the ground failure one has its card down here in the lower left. And so if we look at that card, this actually provides a lot of useful information just at a glance. And for some events, especially if they're a green alert, maybe you don't need to, look any further. It kind of tells you what the landslide estimate is, so how much area is thought to be affected. So that's like the hazard, and then also how many people are in the areas that the hazard is thought to be elevated. So it's a proxy for population effects. And so we have that for landslides and liquefaction, and then we have these colored alerts that go green, yellow, orange, red. And I'll talk about those in a minute and where those come from. Then if you click on the card, it takes you to the more detailed page. And so we have this matrix here. The left column is landslides, the right column is liquefaction. And we have a scale that shows where this event falls on this logarithmic scale that is based on the model results, and some words below it that kind of describe what that means, what the word significant means. And we spent a lot of time carefully crafting these words. And so we have those summaries, and then below that you can click to see the landslide maps. I'm just going to skip that. And so this is what the interactive maps look like. You can turn all sorts of layers on and off. So this is the Anchorage earthquake. You can see the landslide probabilities over here. You can turn on different layers like the shaking contours and the population. And here's what the liquefaction map looks like. And you'll note that our scale bar actually saturates at about 20% probability. And there's a good reason for that. Our models don't actually ever go much above that. And that's because they represent aerial coverage. So I'll give an example of what that means in a moment. But 20% is quite high for these models. And then this is something a lot of people miss. If you scroll to the bottom of the page, there's a download section, and you can actually download the GeoTIFF files of all the different models. So we actually have 5 models that we run. I'll talk about in a minute. 2 of them are the preferred ones that we use for the display on the interactive page, but there's actually 3 others. You can download all the stuff in KMZ format and GeoTIFFs, and you can also get the summary information and so on. There's also ways of accessing this programmatically if you'd like, using our real-time feeds and web services or some of our Python wrappers. Okay, so this is a slide I put together for some of our emergency managers, and I thought I'd just include it here because I like that it summarizes kind of the limitations of this product, because it is a very simple product, and we'll get into what the models actually are in a moment. But it's meant for some things and not for other things. So it's meant for using for situational awareness, before we know what happens. And to give us a quick overall assessment of whether it's likely to be a big ground failure event. It can give us qualitative estimates of things like hazard and population exposure, but not at present do we make any estimates of fatalities or losses. And you can use it as a map to kind of guide reconnaissance to figure out what areas are most likely to have been affected, where might we need to check. And we've actually used our own maps quite a number of times for reconnaissance after earthquakes in the US and in other countries, both in person and virtually. The product is not okay to use as a map of what happened. I've seen some, when we look at what, how it's being covered in the news, sometimes people say, wow, look at this map of all the landslides that happened. That's not what it is. One big mistake, and I'll show why in a minute, is to look at it right when the earthquake happens and not look again, within tens of minutes to hours, because it does change quite a bit as that shake map gets better. And so for some events, it does change quite significantly. It's not for use for any site-specific interpretations. You're not meant to go find your house on it. And then, as I said before, we're not making any actual loss estimates. It's just a proxy for exposure. Okay, so at the core of this product, there are, as I mentioned, 5 models. We have 3 landslide models that we run and 2 liquefaction models. 4 out of the 5 are statistical models based on logistic regression. One of the landslide models, is a kind of heuristic modification of the Newmark method. So that's not the preferred model, but it's one that you can access. So the rest of the models are statistical, and Anna and Jesse made this nice graphic kind of illustrating how these models are made. And so basically we take lots of ground failure inventory data. We take lots of all the different susceptibility proxies that are available globally, that, choosing these is informed by what we know about the science. So we, choose them carefully, but examine lots of different possibilities. And then we basically do logistic regression to get a model, and then we test that model against some other mapped landslide data. And so this logistic regression process is what was used for all of our models. And to get into a little more detail about the 2 primary models that we, these are the ones that are displayed on the web pages. So the liquefaction model both of them use peak ground velocity as their shaking input. The liquefaction model uses proxies for basically wetness of the ground and softness of the ground. So VS30 is a proxy for soil density. That's the shear wave velocity in the top 30 meters. We have global estimates of that are based on slope, and sometimes better estimates elsewhere. And then lots of different proxies for wetness, like precipitation and the distance to water bodies, and global water table depth. And this model is trained on 27 inventories with about 4,000 liquefaction points and 800 square kilometers of polygons. And then the landslide model, which was published in 2018 by Anna Jesse and others. This one uses slope, obviously, and then some different proxies for strength, like lithology. This is a global lithology layer that was published called GLIM. MODIS ground cover, and then some proxies for wetness, and then an interaction term. But this model is really dominated by slope and shaking, which makes a lot of sense. And so this model was trained on 23 inventories, but with 300,000 landslide polygons and points. Though I should note that 200,000 of those are just from the Wenchuan earthquake. So both of these used a lot of data. We tend to have a lot more and higher quality data for landslides than for liquefaction, because it's easier to map, way easier to map almost completely than liquefaction also. But both of them used incomplete inventories, and so the sampling scheme that was used takes an equal number of occurrence and non-occurrence points. And so that gives us a relative probability. And so we want to have, every model would have a relative probability with a slightly different meaning based on how they were sampled, and we want to have a standard meaning. And so we actually recalibrate the output using complete inventories that we have to estimate aerial coverage. And so this, if it will go forward, there we go. So this kind of illustrates the meaning of aerial coverage. This is a 1 kilometer cell. Just for illustration, we actually use 250 meters for landslides and 500 meters for liquefaction in our current models. But just for illustration, this is showing the aerial coverage value, or the landslide probability, of 1%. And you can see that 1% sounds small, but it's actually, a decent number of landslides. This is 5%, and this is 20%. So 20% is like pretty intense landsliding. So even though it sounds small, that's actually not something that we see all that often in the real world. So 20% is high. The models max out at about 30% to 40%, depending on which model. And then to get those aggregate statistics that we use to determine those alert levels, basically we take that aerial coverage value at each grid cell point and multiply it by the area of that cell and just add it up. So that's our aggregate hazard statistic. We do use a threshold of 0.1 g of peak ground acceleration, just to kind of normalize for different shake map boundaries to avoid having large areas of small probabilities, adding up significantly. So that's our aggregate hazard statistic, and that's used to make that that first alert level designation. And then the second one is population exposure. And for that, we just take the probability of each cell times the population estimate in that cell using Landscan data. And then we add that up. So that's where the alert level statistics come from. And the way that we chose the colors is somewhat qualitative, but that's kind of on purpose. So what we did was we ran the model for a bunch of historical earthquakes for which we knew roughly what happened related to ground failure. And we asked some experts, and for landslides, many of you will know the name Randy Gibson. So basically we asked him to do it because he's been to a lot of earthquakes and, you know, mapped ground failure after many earthquakes, and is just kind of the world expert in earthquake-triggered landslides. So we asked him to assign the designations based on what he knew about all these different events. So that's the colors of these dots here. So these are the colors that he chose. And then we tried to find limits for the aggregate hazard and population exposure statistics that lined up most with what Randy's impression of a red versus a yellow versus a green would be. And so that's the process. And then they're kind of roughly order of magnitude, or no, they're exactly order of magnitude bins. For liquefaction, because the areas are much larger for liquefaction, the levels are all order of magnitude higher, actually. Okay, so this project has been running for about 3.5 years. And we have run it as of 2 days ago for 500 earthquakes, and we only run it for magnitude 6 and larger, except in the US we run 5 and larger, and then sometimes we manually run it if there's like a 5.9 in a mountainous area, we might manually run it. So we run 500 earthquakes. It's all automatic. And this is the plot showing the alert levels for landslides with dots and liquefaction with stripes. Like the total number of alerts that we've had. And the overall alert is the maximum of either the hazard alert or the population alert. And so you can see the vast majority of events are green alerts, and that's really useful information to know that these are earthquakes that we don't really have to worry that much about. You also see that there were actually no red alerts for landslides. There were a couple right before we made this tool public, like the Kaikoura earthquake, the Papua New Guinea earthquake, and the Palu earthquakes. And actually the Palu earthquake happened the day that we were turning this tool live, like when we were making it public. So we can't really count that one, but it was kind of ironic that it was the day that we turned this on. So let's see, and then the median post time is about 30 minutes after the earthquake. And that is somewhat controlled by pager, because we actually wait for the pager loss estimates to be posted before we run ground failure. And that's because pager has a human who reviews the shake map and the results to make sure they look okay for significant events. And so we're just taking advantage of that. So it adds a little bit of a delay, but 30 minutes is still pretty good. This is a map of all of the alerts that we've issued for landslides since October 2018. The circles are the hazard alerts and the stars are the exposure alerts. And this is a map of all of the liquefaction alerts that we've issued since in that time as well. And you can see that liquefaction did actually have some red alerts in Japan, and there were quite a few in the Philippines, and then actually 2, there are only hazard alerts, not exposure alerts, in the Amazon in South America, which is a very wet place. We don't know if any liquefaction happened there, but it's wet. We actually had quite a few, maybe a little more than we'd been having, quite a few earthquakes in the US that had significant ground failure potential. So the left plot here is showing the landslide alerts in the US, and you can see most of these, except for the Puerto Rico earthquake, were just hazard alerts. They were in most cases, the landslide hazard was quite remote. In Puerto Rico, the landslide hazard was actually green, but the alert was yellow because there's a lot of people in those areas. And the liquefaction alerts shown at right are, similar earthquakes minus Idaho. And the Salt Lake City is included here, and it did not have a high landslide alert. So we've been kind of keeping track, as earthquakes happen, we're always checking news reports. Sometimes we look at satellite imagery. Sometimes we, look in more depth than others, but we kind of keep track of what we know happened after major earthquakes worldwide. Most of them will not have an inventory that's published, sometimes for a few years. So a lot of what we're going on is basically news reports and satellite imagery, unless we go in person like we did for the Puerto Rico earthquake here. And we found that overall, obviously with some exceptions, that the alert levels are usually pretty spot on, or as spot on as you can be for a qualitative measure. But yeah, we're pretty happy with the alert levels and, how they've been performing relative to what actually has happened. The models themselves, they're extremely simple, as you saw, very coarse resolution. When the shaking estimates are relatively well constrained, which is not the case everywhere. But when we have, like some seismometers nearby, when we have lots of did you feel it reports, if we have a good estimate of the fault, then the models actually perform pretty well, especially identifying the areas of high hazard. So this map at here, I changed the color scale just so I could show landslides and liquefaction on the same plot. This one at left is the orange is a landslide probability for the Kumamoto earthquake in the Aso caldera, showing a landslide inventory that was mapped for that. And the one at right is the Hokkaido earthquake, showing liquefaction in the purple colors and the landslide model in the orange colors. And so we find that it usually can identify the areas of high hazard reasonably well, but it also identifies a lot of areas that have elevated hazard that don't have landslides. So it's not as good at removing areas where landslides are less likely. Same with liquefaction. This is a massive area that had elevated liquefaction probabilities. We don't have a complete map of what occurred. We know there was liquefaction here and here for sure, but generally the models tend to overpredict a little bit, but they do tend to capture the areas of highest hazard. I won't get into too many details, but when you run an operational product and we're always looking at the results and comparing it to the news and imagery and stuff like that. And so whenever you're making a new product, there's always unexpected things that come up. And so we did find, and this was mostly during the internal testing period, we found a couple of weird things that came up related to the models themselves and then some of our implementation of it that we basically fixed manually. So this is one of the cases. So this is the Hokkaido earthquake. This plot at right, this is a map of all the landslides that were triggered by that earthquake. This plot at left is the original ground failure model. You can see this area with the hashed line has very low probabilities, even though there's lots of landslides in there. And it turned out that this was mapped as unconsolidated sediments in the geologic map. And because of the way the sampling was done, sampling of the inventories, that unit barely got sampled at all because most places that are unconsolidated sediments are flat. But this area has a lot of hills that are covered in tephra. So it was, very weak in an earthquake, but because of the way the sampling was done, the unconsolidated sediments, the model thought statistically that it was the strongest unit, and we didn't catch that. But then in the Hokkaido earthquake, it became very clear that we had to change that. And so we manually adjusted that, and now the model looks a lot better compared to the actual landslides that happened. This is another case that we saw where we had not clipped the range of the data to the range that was used to make the model. And so Papua New Guinea is extremely wet, way, way wetter than any place that we had any data in the data sets used to create the model. So the precipitation was off the charts, literally. And so during this testing period, we saw this event come up where it said basically all of Papua New Guinea would liquefy because that high precipitation value dominated things. So we had to, we should have done it earlier, but it's good that we caught this. We clipped all the input layers to the range of the data that was used to make the model. And then we also added some shaking thresholds for liquefaction because the model is not as sensitive to shaking as you might think it would be. So some of the other input layers can also influence it pretty significantly. Another thing that we've kind of known about from the start is that, you know, landslides are a continuum. Our ground failure is a continuum. It starts, you know, you have some landslides on steep slopes and then shallower, and then you can have lateral spreads and flow slides in very gradual slopes, and then you can have liquefaction and flat slopes. So we actually kind of have a hole where the flow slides and lateral spreading happen. You know, they're sort of captured by the liquefaction model if they're on small topographic features, but this is one case, like a dramatic case that you've probably heard about, the Palu earthquake in Indonesia, where these massive flow slides on very gradual slopes. This slope here is about less than 3 degrees. These massive flow slides happen related to liquefaction on shallow slopes. So here's a before and after. Note you can also see the fault slip in the imagery. So this was really a really terrible landslide. About 1,000 buildings were in here. Lots and lots of people were killed. And this is the map of that valley. This is the Balaroa slide over here. The red is the landslide model. The purple is the liquefaction model. And these are 2 other large flow slides that also happened that were very similar. And these kind of happen, you know, they're in the liquefaction zone, but they're kind of on the boundary between the landslides and liquefaction. So at some point, you know, if we have enough data, it might make sense to have a third model that kind of covers this in-between area of the landslide continuum. Okay, and then lastly, I just wanted to talk about the evolution of the shake map, because I think this is something people don't know that much about. So as I said, the shake map keeps getting updated as time progresses, and it can change quite a bit. And most earthquakes start as a point source. And for large crustal earthquakes that have extended faults, a point source is not a very good approximation. So this is showing the Haiti earthquake that ruptured from east to west on a fault going over into the middle of all these landslides. These black dots are landslides from inventory that we mapped, that Martinez et al. Inventory. And you can see the initial model from a point source only has landslide probabilities to the right, or to the east over here. Oops, wrong direction. But then once we add in a fault geometry, and in this case, about 3 hours in, we had a fault estimate from teleseismic waves. Then it kind of starts to look a little closer to where the landslides happened. But this event, it's not until we got INSAR data where we could see where the fault ruptured and where decorrelation occurred and so on, where we could really get a better fault geometry in there and have a better ground failure model. And that, in this case, took about 5 days to get that better constrained model. So as a result, on average, this like addition of the finite fault model, on average, our alert levels increase a little bit. So this plot here is showing the ratio of the final aggregate hazard to the initial aggregate hazard. No change. Most events don't change. So that's this 0 line. I'm not even showing those. But these ones to the right of the black line are events for which the aggregate hazard increased. And the ones to the left are the ones where aggregate hazard decreased. So you can see that more increase than decrease on average. Okay, so I only have a few minutes left, so I just wanted to talk about a bunch of work that the USGS and collaborators are doing to kind of build on the stuff that I just presented, because what we currently have is what we basically called our like simplest initial product, and we want to, you know, build on it from its current simple. And so there's a lot of different directions that we're going. So I'll just talk about a few of these. So one thing that emergency managers have expressed interest in is knowing where infrastructure might be affected by ground failure. And so we had an NSF intern, Bradley Wilson, who led this effort to take the existing ground failure model, OpenStreetMap roads, and then he used all these landslide inventories to basically calibrate this. He found where those inventories intersected roads so that we had road intersection data points. And he calibrated the road segment and the average landslide probability along each segment to estimate the obstruction probability. And so this is not operational yet. We have the codes are released, but it's not part of the suite. And we have the potential to expand this to other types of infrastructure as well, as makes sense. Another thing that I alluded to earlier is that we want to be able to estimate losses from ground failure and incorporate those into pager and shakecast. The reason that's really difficult is that there's not great compiled data sets. They don't often separate landslide or liquefaction losses from total losses. But fortunately, our colleagues at Indiana University have been working on compiling a lot of landslide fatality data, and our colleagues at Tufts University are doing the same for liquefaction loss data. And so we took the fatality data set and all the events that we had data for, including those that had 0 fatalities. We ran the ground failure model, and that's what this map here is showing, is all the events that we ran this ground failure model for. So these are historical events, all the way, some as old as 1918 to the present, that we have some landslide loss data on. So these are all in CompCat. You can see the products if you go to the event pages for all of these. These are what the alerts look like for those. So, lots more red alerts in historical times than just in the past 3 years. This is the population exposure alerts. And we started to look at this in a simple sense, and we have a student who's working on doing something more in depth right now. But this plot is just showing that the relation between the population exposure from the models for all these historical events compared to the number of landslide fatalities. And you can see there's a lot of scatter. I've levels just to make it a little clearer, and added these bars that kind of show the range of values within each alert level bin. So we can get an idea of, like green and yellow population alerts tend to have, 0 to 8 fatalities, orange 1 to 400, red, 50 to 10,000. But this is just kind of a starting point for estimating losses. And you'll note that, so these larger circles are deep earthquakes. So these events here are all very deep earthquakes, a lot of them in Afghanistan that had fatalities, but we have 0 population exposure. And that's because for deep earthquakes, if the shake map doesn't have constraints, the shaking is probably less than our 10% G shaking threshold. So obviously there's something we need to address there. Another thing that we're working on, and this is, a lot of people are involved in this. I'm showing some figures made by Davis Engler and Paula Berge. Paula is a Mendenhall postdoc with us, and Davis is a mathematician who works with us. So we're working on, basically for parts of the US where we have better susceptibility data, we're working on a framework for updating the global models using that better susceptibility data when it's possible. And so this example here is showing the Loma Prieta earthquake. And basically the concept is that we have really high resolution superficial geology maps showing this is artificial fill in the Bay Area. This is mud in the Bay Area. And we have all these CPT data points. So CPT is cone penetrometer testing. So that's when you push a cone into the ground and measure continuously as you're pushing it into the ground. That's one of the primary tools for evaluating liquefaction hazard. So we have a lot of data from within these different units, and so we're aggregating the data and computing something called the liquefaction potential index for each different type of geologic unit, and then we're actually using that to update the ground failure probability from the global model. And so this plot here at right shows where the probabilities got higher. That's the red areas when we added this this approach, and where they got lower when we did this Bayesian updating. So this is work in progress, but it's basically a way to get higher resolution hopefully higher quality results in areas where we have better data. Our colleagues at Tufts and Indiana University, who have, they're the ones who led the effort to develop the original models that we're currently using, they're continuing to improve upon those models. And so they've got some preliminary results published in some technical reports, but these are still works in progress that we're not quite ready to use yet, but they're working on things like using higher resolution slope data, using new geologic proxies or new susceptibility proxies that have become available globally, using more and more inventories and so on, and more rigorous uncertainty estimates. So these hopefully will be coming in the next few years. Another effort that we've been working on, starting back in 2015 or 2016, is making these inventory data sets available and accessible all in one place. And the idea is that, so like the PhD students, Ananoki Jesse and Jing Zhu, they each spent a lot of time just emailing people and asking them to share their inventories. And we just didn't want anyone to repeat that. And we wanted to promote research, because if somebody else wants to make an awesome model that we could use, then that's great. So we made this open inventory data set that we continue to update. Robert Schmidt, who is a GIS specialist here, kind of maintains that. And he also made this really neat web application, which I know some people have used, for their classes to make activities and so on. So it's a really neat web app where you can go in and browse all these inventory data sets. And so we're working on an update for that. It's in press, basically version 4. So we should be up to, I think, 50 something earthquakes that we have inventories for landslides, and 11 for liquefaction. We also do a lot of work on collecting new data sets, new or old data sets. So we do reconnaissance after Earth. We sometimes map inventories from satellite imagery and so on. But one thing that, this is being led by Sonia Ellison, one thing that we're working on right now is to dig into the past and actually get some, basically, dig into the past before the digital era, when we had a couple, quite a few important ground failure events in the United States, and to turn all that data into actual digital inventories. And so Sonia's been working quite hard on this over the past 2 years or so, and she's working on the Great Alaska Earthquake, which is one of our biggest ground failure events in the US, and the 1906 San Francisco earthquake. And so we actually have pretty good shake maps for these, because there's a lot of observations and historical records on what people experienced, and you can use those intensity estimates to update shake map. So we want to dig into the past. We're making new inventories. We have several talented remote sensing specialists now working with us. So we're always exploring ways of getting better maps of the ground failure that occurs using remote sensing methods. And as you know, like some techniques work in certain settings and some don't, vegetation, snow, light, all sorts of things affect that. And so we basically have been throwing everything at it. So this paper at the left was led by Sabrina Martinez. And we tried a whole bunch of techniques for the Anchorage earthquake to just try to map everything we could. That was a very difficult earthquake because of snow and darkness and vegetation. This at right is some preliminary work that Paula Berge, one of our postdocs, is working on with the Ridgecrest earthquake. And so she's been using INSAR techniques and optical change detection and INSAR change detection to try to more completely map what happened in the Ridgecrest earthquake. This is Searles Lake right here, showing surface manifestations of liquefaction and some lateral spreads in the lake. So we're just discovering with this event in particular that liquefaction happened over a huge area that I think we don't often get to document. Just wanted to mention is work that Dave Wald is doing with colleagues at Stanford and Stony Brook, where they're using some of these remote sensing techniques, in this case, a damage proxy map, which can be generated rapidly after a major earthquake, within a couple of days, and using that to update these ground failure models. So this is an example from a conference paper that they have cited here for the Hokkaido earthquake. And this was Hokkaido earthquake was a really nice example because the damage proxy maps worked really well here. So this is where they took the prior ground failure models, landslides and liquefaction, and then this is where they updated it using this damage proxy map, and then you can compare, these are observed landslides, and so we can actually start to, move even closer to the truth as time passes after earthquake happens by updating. So in that, with that, I think I'll wrap things up. I don't know, I hate to read my conclusions out loud, but hopefully I showed that, we've learned a lot from the past 3.5 years of running this product. We've run over 500 earthquakes. It seems to work reasonably well, but there's things we can improve and that we're working on. And yeah, just wanted to say thanks again to all the many, many people who've contributed to this. So with that, I guess I will end. I just realized my slides weren't being shared anymore, but here we go. Okay, sorry for that kerfuffle at the end.
Thanks, Kate. I can't believe we lost power to the entire building and we were able to connect back within a minute or two there. So
did we drop off? Does anyone know if we dropped off or were we here the whole time?
I'm not 100% sure, but the recording still is going and everything, which is great. So we can look in video evidence of exactly what happened.
You have to remove when I was swearing.
yeah. Jamie can do the editing for us. So I do see the chat window starting to appear, and I see at least one question. I'm going to look for hands up as well. Kate, I'm just going to start off with a quick question. This is probably a question that's difficult to have a concrete answer to, but when I looked at your plot of kind of exposure versus landslide hazard, where you did those kind of historical runs and you kind of looked at where those fit within that kind of scale, I noticed that in your kind of lower population exposure and lower landslide hazard, there were like fewer events to constrain that kind of that green area compared to up in the upper right hand corner for the higher end. Seeing all the different ways that you guys are attacking updates to the model and future work, you're really taking everything on from newer inventories to new inventories to also kind of newer global raster data. And I was wondering, your thoughts on with the current model, the current logistic. Are you feeling like you're seeing incremental improvement, higher improvement, kind of with the availability of kind of higher resolution global raster data that these kind of susceptibility indices that you mentioned, or the addition of new inventories, particularly things that might fit in that kind of lower kind of green range? Do you think those might drive the bus more in terms of how the model behaves right now?
Yeah, so I think having more data sets for like very mild to non-events documented is really important, but people just tend to only document the really extreme, exciting ones. So that's something that we're actually, trying to do on our own, is to compile more of these null events so that we can better constrain things on the lower end of the aggregate statistics, but also better constrain things, in the maps, so that we're not, I don't know if I have that figure handy, this one, so that we're not over predicting as much and that we can better constrain, where the hazard is high and where it's not. So I think as far as improving the maps, I think time will tell. I'm hoping that this updating approach that we're doing regionally within the US will, demonstrate that when we have higher quality susceptibility data that, better speaks to the susceptibility to these types of ground failure, that they'll actually perform better, and then maybe we can do something similar other parts of the world. But yeah, I guess I don't really know yet exactly what input data sets might improve things. We've got, Paula's looking at different soil moisture, remote sensing products, and just like digging through because there's so much out there right now as far as remote sensing products and, globally available proxies. And there's just like so much out there that it's kind of overwhelming. And so we haven't really explored a lot of that yet. And I'm hoping that it'll help improve the models.
Thanks, Kate. I'm going to start working through the questions that have popped up in the chat window. I see 3 right now, and you might have the ability to see the chat window as well, depending on how your screen is shared. But I'll try to read the questions slowly, and if you're not catching all of it, just let me know. The first question is from Don Lindsay. He says, nice job covering the power outage. Are the effects of topographic amplification resulting in increased PGA and landslide activity covered under the interaction term between the slope and natural log PGV in the landslide regression model? Or is the model too coarse to address topographic amplification along narrow ridges with steep side slopes?
So we don't explicitly account for topographic amplification right now. So there aren't really great ways of simplifying it. The shake map will account for it. Like, say a seismic station is on a ridge and we're using that seismic station in the data, like that'll be in the shake map. But there aren't really, like, topographic amplification is so three-dimensional that, you know, we haven't really seen great ways of simplifying that to estimate it directly. There's a few papers, but honestly, the amplifications aren't that big in those papers where they've, you know, done numerical modeling and so on. It is, you know, it's probably in the slope interaction term, you know, that maybe accounts for it to some extent, but that's just slope. It's not the shape of the ridge or the frequency that the shaking is at, you know. So it's a very, very simplified way of accounting for it, if anything. So that's another area of, you know, future work just in the shake map itself, as if, you know, we could potentially work on ways of estimating topographic amplification better.